You're looking at an uncoiled cochlea containing a basilar membrane floating in endolymph. The organ of Corti, which contains the auditory receptors, sits upon the basilar membrane. Movement of the basilar membrane stimulates the auditory receptors. Notice two structural properties that determine the way the basilar membrane responds to sound. First, the basilar membrane is wider at the apex than at the base by a factor of about 5. Second, the membrane's stiffness decreases from base to apex, the base being about 100 times stiffer. When a sound wave pushes the footplate of the stapes at the oval window, endolymph is displaced within the scala media, the chamber containing the basilar membrane. Movement of the endolymph makes the basilar membrane bend near its base, starting a wave that propagates toward the apex. The distance the wave travels depends on its frequency. This high-frequency wave vibrates the stiff base of the membrane a good deal, but most of the energy is dissipated before the wave propagates very far. Now notice the difference in the traveling wave generated by a low-frequency sound. This generates a wave that travels all the way up to the floppy apex of the membrane before the energy is dissipated. These vibrations in the different parts of the basilar membrane establish a place code for sound frequency. This is because different locations on the membrane are maximally deformed at different frequencies. This mechanism is responsible for neural encoding of pitch.